So whether a satellite is orbited by the Earth, what factor will the time required for a single orbit be multiplied if the radius of the orbit is doubled? Okay, so the satellite's going around the Earth. So if you double the radius, assuming the velocity stays the same, if you double the radius, what do you do to the circumference? Yeah, good. You're going to make it bigger. By how much? Circumference equals 2 pi r, yes? So if you take a second circumference, which is 2 pi times 2r, meaning we doubled it, then basically we've done 2 times the original circumference, right? And assuming the thing goes at the same velocity, then 2 times the circumference would be twice the time, because it has to travel twice the distance. So for A, my guess would be 2 times the time. Then for part B, if the mass was tripled. Now let's see, let me think about if you double the radius. See, it depends on what they're asking for, because if you double the radius and you want, okay, let me see if I can do this. Here, so this satellite S is at radius r. So if we do another one, and now the satellite S is at 2r, the path is twice as big. The question is a bit ambiguous. If it's a weather satellite, is it in geosynchronous orbit? Did anybody look at the answer? Because if they say doubled, then they mean they want the same velocity. Did it say doubled, or do you know?
It says if m2 equals 3m, then the period t stays the same.
Oh, no, I'm talking about part A. Sorry.
Oh. Sorry, were you asking it?
Yeah. For part A, what did they say the answer was?
2.83.
Okay. So then what they actually want is they want a geosynchronous orbit again. So then that means what velocity is going to keep us in geosynchronous orbit. And I don't know if you remember when I was talking about that. Geosynchronous orbit is the square root of big G m over r. Remember this? This is mass of the planet, not the mass of the satellite. So this velocity here, that's like v1. So then v2, that's like v1. So v2 is the square root of big G, mass of the planet, over 2r. Okay, so that's the new velocity. Okay, so that's the velocity it needs to stay at that height. And so then the time will be distance over velocity. And the distance is, of course, sorry, I shouldn't have done 2 pi. I should have said 4 pi r. Right, because it was 2 pi of 2r. And then dividing that by big G, mass of the planet, over 2r. Okay, so that's the time for 2. The time for 1 should be 2 pi r over the square root big G MP over r. Have I lost anybody? Do you see what I did? Okay, so in order for this satellite to stay in orbit, it has to have this minimum velocity. No. Yeah, in order for this satellite to stay in orbit, it has to have v1. In order for this satellite to stay in orbit, it has to have v2. And then the time that it takes to orbit will just be the circumference divided by the velocity. And then they said, how many times bigger? What will the time required for a single orbit be multiplied by if the radius of the orbit's doubled? So then how much bigger is the second one than the first one? So then it's kind of like we're saying, oops, I should probably use a pencil. we're saying something like T2 equals blank times T1, right? And then the way we can do that is we can just take T2 divided by T1, and that's going to give us our number blank. So T2, again, was this. So T2 is 4 pi r divided by square root of big G m over 2r. And that's going to be divided by 2 pi r over square root of big G m over r. I just divided the times. So then the pi r's go away, the 2 pi r's go away, that just becomes 2. And then when I invert those, so then that becomes 2 big G m over r divided by big G m over 2r. So then that becomes 4 big G m over r divided by big GM over 2R on the bottom. Well, that's irritating because that cancels. You said it was 2.8? 2.83. Why am I getting not that? The R's will go away, but then I have a 2. I must have made an algebra error. Oh, this is from the solution?
You printed it out.
Nice. 2 pi over v. Oh, nice. You used Kepler's law. Okay. Yeah, we used all the same things. Big G m over r squared. Okay. Like I said, my logic is sound. I must have made some simple math error. Does it make sense to you that this is supposed to be some number n? Well, what I did over here was I squared everything, right?
Oh.
But I have to do that to both sides. So what I get is 8 equals n squared. And what is the square root of 8? 2.8. So we get our answer. Yay. Universe is in order. I have not failed, which is excellent. Okay, so again, what did we do? The solution in the book is basically take Kepler's law. Use Kepler's law for the two positions, and then that's it. But again, what did we do? We said this thing, when it goes to a higher altitude, if it wants to stay in the same location, then it has to have this v2 velocity. At the lower altitude, it has this v1 velocity.
Selling tickets. Mr. McCone, sorry to interrupt.
What's that? Oh,
Sorry to interrupt.
yeah, I already bought mine. Sorry, dude. Anybody else?
All right. Today we're going to buy parking tickets.
Okay, yeah, so does everyone see what we did? How did we come up with this? Just as an aside for that, we came up with that orbital velocity. Okay, that's just crazy. It looks crazy. Okay, let me erase that. We came up with the orbital velocity. The orbital velocity came from saying that the force of gravity is going to be equal to the centripetal force on that satellite. So we said just kidding, that's not true. We said big G, mass of the planet, mass of the satellite over r squared is going to equal to mass of the satellite, v squared over r. Right? So we canceled one of those, canceled this, and we said v is equal to the square root of G times big M over r. Right? That's where I got that from. I think I talked about this when we were doing the lectures. But, so this says gravity is what's supplying centripetal force, so that's the speed you need to orbit. So then I'm saying that's V1, that's the original orbital velocity. If we double the radius, now the orbital velocity is this, right? It's the over 2r. And then I said, okay, well, time is the distance over velocity. So I take those two terms, and then I said, well, it's just a fraction. And I need to see what the number was. And then my error, or whatever, my peccadillo, was that I forgot that this number, if I square one side, I have to square that side. And then when I remember to do that, we get our right answer. Okay? Yeah.
So that n squared equals 2?
What's that?
Like, where did you get 8?
Where'd I get 8? Oh, no, see down here with the 2? If there's
Oh,
yeah, that 2 goes up on top, but that's good. Thanks for asking. Okay? Then, so if we go to the second part, its mass is tripled. Look at that equation, V1. Does that have the mass of the satellite in it? No. So, boom, no effect. And then for C, it is instead placed in an orbit of the same radius about Mars. So now we're looking at, we want to know the T2 over T1. Oh, in this case, it's not really T2, is it? It's T Mars over T Earth. And then that's going to give us some number n that we're looking for. Okay, and then T Mars is going to be, I'm assuming it's the same radius, so it's just going to be, it's going to be like the bottom equation, right? It's going to be like this, where we took 2 pi r divided by that. So for Mars, we're going to get, okay, why did that do that? Oh, crazy. All right. For Mars, we're going to get 2 pi r divided by square root of big G mass of Mars over the radius, and then taking 2 pi r over big G mass of the Earth over r. Now, obviously, we can see that goes away, and this becomes the square root of big G mass of the Earth over r, square root big G mass of Mars over r, right? So if we square that, that equals n, right? And we square both sides, then the G and the r goes away. And then so we get n is basically equal to the square root of the mass of the ratios. So the mass of Earth divided by the mass of Mars. So the square root, mass of Earth is about 6 times 10 to the 24. Oops, it's not 6 times to the 24. That would be a pretty small mass. Oh my gosh, I did it again. 6 times 10 to the 24 kilograms. And they told us Mars, right? Mars was 6.6 times 10 to the 23rd. So 6.6 times 10 to the 23rd. So basically it's 60 divided by 6.6, which is around 9. So this is going to be around 3, right?
Yes.
Yeah. It's a 10 because I have crappy handwriting. That's why it's a 10. So let me fix that so people. There, how's that?
Why did you solve for n in the last question?
Why did I?
Yeah, or when we were on B.
Oh, because that's what they were asking for? See, because they asked this. They asked, what do you multiply? Like, what multiplier, how much bigger is the second time than the first time?
Oh, okay.
Right? And so I interpret it as that. T2 is equal to blank times T1. And then so I said, oh, well, look, that number, this number n, is T2 over T1 to create a simple math fraction there. Yes?
So part C, it was asking if the satellite, if the